Hey guys, today we are discussing the question how we can create a priority queue using a heap data structure. Okay, so we have been given certain functions and we have to write the body for them and implement them using a heap data structure. So let us discuss how we can implement a priority queue using a heap. So heap is basically a binary tree. So something like this. But the thing is, this is different from the traditional binary trees in the manner that heap follows two very special properties. Okay, so heap has two properties, two very important properties. First of them is heap order property, and the second one is complete binary property. Now the thing is, the operations of a priority queue are performed in a certain time complexity. That is, add and remove operations for the priority queue are performed in log n time complexity, and peak peak operation is performed in constant time complexity. That is O1. So this is where these properties allow us to perform these operations in this certain time complexities. So heap is very useful to form a binary tree. How these properties help and what are these properties, that is what we are going to discuss next. So first of all, what are these properties and why do we use them? So let us begin. So the first one is heap model property. Okay, so the thing is, a tree in a binary tree, if every parent has a higher property than all its children, then the tree is supposed to be following the heap order property. So what I mean by that is, let us say for this tree, okay, so as we know, by default, the smaller the value, higher is its priority. So for a priority queue, by default, smaller its value, higher would be the priority. So which means every node which has smaller value would have higher priority. So in this case, as you can clearly see, every parent has higher priority than its children because the value of the parent is smaller than its children. So here we can clearly see 30 is smaller than both his children, that is 60 and 70, and same for 20 and same for 10. 10 is smaller than 20 and 30. So for a tree like this tree is need to be following heap order property. Okay, now how does this help us? Why do we use this property and how does this help us in achieving these time complexities? So let us say we were supposed to perform peak operation. Now what would peak operation do? So it would return the element with highest priority, right? Highest priority. So let us see which element here would have highest priority. So as I said here, that smaller the element, higher would be the priority. So the smallest element in the whole tree would have the highest priority. Now which is the smallest element among these? This is the smallest, right? So you can clearly see that the root of the heap would always have the lowest value, and that is the root would always have the highest priority. That is, in any heap, the root will be the element which would be returned if we call the heap, if we call the peak method. So which means that we always know where the root is. Now after I explain the next property, we will see how this is done in one time complexity. So let us start. The second one is complete binary tree property. So what this property allows us to do is, it allows us to make a tree using an array list. So let us see how that happens. So let us say we have an array list like this. So now you will ask the question how we can make a tree using an array list. So this is just a means of visualization, right? You can just visualize this array list as a tree, right? So for example, if we move like this, you can clearly see we are moving the same order as this array list. So this is 10, this is 20, 30, 10, 20, 30, then 40, 50, 60, 70 in the same order. So what we can say that we can easily visualize this array list as a tree. So that is what is happening here. We are using a array list to form a tree. That is the heap data structure. Okay. So now the thing is, we can clearly see that the root is the first element of the array list. So now this is where the peak properties has over time, because we always know where the root will lie, because it will always be the first element in the array list. So we can easily get this. We just have to use arraylist dot get 0, because 0 is the first element, so we'll always get the first element using this, and this is done in O1 time complexity. So this is how the peak operation works for this. Now I haven't explained what this complete binary tree actually means. So and why this allows us to make tree using array list. So a complete binary tree is basically a binary tree where only the last level is allowed to be incomplete. What I mean by that is, for a tree like this, let us say we draw more fields. Now as you can clearly see, this tree is not complete because I mean it is a complete binary tree, but the last level is not complete because it has missing childs, right? These children are not present. So the thing is, for a tree to be complete binary tree, only the last level is allowed to be incomplete. So here only the last level is incomplete, so it is a complete binary tree. But if suppose we remove these children, now this is not a complete binary tree. Here the second last level is also incomplete, so this is not a complete binary tree. Okay, so for a binary tree to be a heap, the tree must be a complete binary tree, and that is why it allows us to create a tree using an array list, because since the tree is complete, we can write indexes for the nodes. For example, let us see like this: 60, 70, let us say 80 and 90. So what we can do, that we can visualize this as the array list. Okay, 20, 30, 40, 50, 60, 70, 80 and 90. So what we can say that, since in array list we can easily we have index for all the elements like 0, 1, 2, 3, 4, 5, 6, 7 and 8. What we can do is we can assign indexes to the tree also. So this is 0, 1, 2, 3, 4, 5, 6, 7 and 8. Now what we can see from here is that not only we can get the indexes of the children, but we can also get the index of the parent itself. But as we know earlier, while we were making trees using the node class, we were only able to traverse to right and left children. We weren't able to go to parent. Okay, so this is where this array list is very helpful to us, because it allows us to get our parent also. Now by visualizing this, we can clearly realize that left left child index is nothing but 2 into parent index plus 1. So as you can see from here, for 1, 2 into 0 plus 1 would be 1, 2 into 1 plus 1 would be 3, and 2 into 3 plus 1 would be 7. So this is the formula for left children index for left child, and for right child it would be 2 into pi plus 2 for right one. Now the thing is, we can easily see the parent, we can easily get the parent index if the index of the child is known. So what would that be? This would be li minus 1 upon 2. So this is the formula that we are going to use throughout to get the index of the parent. Okay, now we have seen all both the properties. Now we are going to see how remove and add operations work and how they are done in log and time complexity. So first of all, we are going to see the add operation. Okay, let us see. So let us say we have been given the tree that I have been drawing so far, this only. Okay, so let us say we were supposed to add an 80 to it. So this is nothing but array list, right? So 20, 30, 40, 50, 60, 70. Okay, so this is the initial array list. So to add 80 to this array list, all we have to do is arraylist dot add arraylist dot add 80. This would add 80 to the array list, and if we do this, this would again completely follow both the properties, because this is a complete binary tree and this also follows the heap order property because all its parents are smaller than its children. So but the thing is, what if we were supposed to add a node whose value is smaller than the already existing elements? That is, for example, what if we were supposed to add 5? So if we add 5 here now, because if we perform add operations, the element would be added to the last. So here element is added to the last. So what would happen is that now it violates the heap order property. It is not being followed. So we have to perform certain operations such that this this again continues to follow the heap order property. So to do that, we are going to use a functionality, or basically algorithm, or you can say as a heapify. So we are going to perform up heapify, and what this would do is after an add operation, it will allow us to regain the heap order property. And how does this happens is that after adding, since this ls.add would work in over time complexity, so after adding we will check if the element which is added has a lower value than its parent. If this happens, what we are going to do is we are going to swap them. So we just swap them. So how do we swap this 5 with 40? I stated earlier that we can easily get the parent index using 2 into child index minus, no, actually it was child index minus 1 by 2, as I wrote earlier, right? See here. Okay, so since we know the index of 5, because it is added to the last of the array list, so the index would be size minus 1. So since we know the index of 5, we can easily get the index of 40, right? So if we get the index of 40, so in this case it would be 0, 1, 2, 3, 4, 5, 6, and here let us say the index of 5 initially was 7. So what would be the index of parent? It would be 7 minus 1 by 2, which is basically 3. So we have gotten the 3. So now since we have got the parent index, now all we have to do is we have to perform swap operation between these two elements in the array list. So this would be swapped here and this would also be swapped in the array list too. So 40 would come here and 5 would come here. Now one thing I want everyone to understand is that I have said that every parent should have a smaller value than its child, but I haven't said anything about how the values of children would be written. So it is very well possible that the left child could be bigger than the right child. We only have to consider the parent and the child comparisons. We don't have and we don't care about the values of children among themselves. Okay, so we can easily write 150 here, 50 here, that would be valid too. Okay, so this everyone should keep in mind is that there is no constraint for how the which child would be on the left, which child would be on the right. Okay, so let us proceed now. After swapping, we again call the heapify function, and what it would do is check to its new parent. So what is its new parent? It is 20, so it will check with it. Is the value of the parent is the value of parent greater than its child? Yes, it is. So what we are going to do, we are going to swap them. Okay, so let us just swap, and we get here 20, we get here 5. The same thing would happen in the array list. We get here 5 and we get here 20. So here we write 20 and we get here 5. 5 comes here. Now again we again call the heap5 function. So what would this would do, it would again check and it would again swap, because 10 is smaller than 5, 10 is greater than 5, so 5 would come here, and here we would get 10. And the same thing would happen in the array list. We will get 5 and we will get 10 here. So until when this heap5 function would run, this would run until either we reach the root node, or we have we get a value which is greater than its parent. For example, let us say I tried to add 15. So if I add 15, it would be added here, because it is complete binary, so we can't add this here. It should proceed from left to right. Okay, I forgot mention this, but for a tree to be complete binary, if we add a new node, it should proceed from left to right. We can't just add the new node here. Okay, this is not correct. This would violate the complete binary property. So what we can only do is we can add them from left to right. So the next node would be added here, after this added here, then here, then here, and then so on. Okay, so it should move only from left to right. Now let's see here. I have added 15. So what this would do, I would again call heapify up heapify. It would check if the value of parent is greater than the current element. It is greater than the current element, so we are going to swap them. So 15 is swapped with 50. So here 15 comes and here is 50. The same thing would happen here. Here would get 15, and in the end I would add 50. Okay, so here I would add 50 and here we get 15. Now if you see it again, if I call this function again, it would compare if it is smaller than its parents. It is not, right? So this is where swapping stops. We don't have to check further, because the rest of the tree is following the heap order property. We only have to do it until now. So this is where the up if I will stop. Okay, so this is how we add an element. So now let us examine how this is running in log n. So as we can clearly see that the addition, we are performing two functions here, two jobs here. So first one, we add to the array list, so this is done in one time complexity. The second one is we are performing up heapify. So what we are doing is we are traversing the tree itself. So what is the length of the tree? It is nothing but log n. So for up heapify, when it runs in the whole tree, its complexity would become log n. So for up heapify, the complexity is log n. So basically overall complexity is nothing but log n. So that is why this heap allows us to perform the add operation in log n. Now let us understand how remove function works. Okay, so what remove function does is that remove function returns us the element with highest priority, and it removes it from the list. So peak did was just to show us what is the element with highest priority. It didn't change the array list. But what remove would do, it would actually give us the element with highest property and remove it from the array list. So let us see here. So if we 40, so if we use the remove method here, what it would do, it would actually give me 10. Okay, because 10 is the highest priority element here. So when we use a remove method, we'll always get the root node. Okay, so now how do we achieve this in log n time complexity? So if we use remove, we can only perform this is in over complexity only if we are removing the last element. If we are removing the last element, we can do it in overtime complexity. Otherwise, for every other element, it is done in overtime complexity, which is greater than log n time complexity. So we don't want that. So what we are going to do is to get this in overtime complexity. What we are going to do is we are going to swap the root node with the last node, because we can remove this 70 in overtime complexity. So first of all, let us swap them. So this would become 10 and this would become 70. Now what we'll do is we'll just use Arraylist dot remove. Okay, so let me write this clearly. So the first thing that we did was we swap element at 0 and size minus 1. Size minus 1 is the last element. Now second thing that we are going to do is we are going to remove the element at the last, so basically element at size minus 1. So what this would do is remove 10 and we are going to return this value. So we have gotten the highest element, highest priority element, and removed it from the list. But what we can clearly see that now this element violates the, this tree violates the heap order property. So we have to again perform certain operation to regain this property. So what we are going to do here, after every remove operation, we are going to perform down heapify. Okay, so this would be done from upwards to bottom, and upify is done from bottom to upwards. So let's see how that is done. So first of all, what we are going to do is we are going to get the index of both its children. So we can easily do that by using li is equal to 2 into pi plus 1, and for right child it was 2 into pi plus 2. So if we use this, we can get the index of these two. For example, this index is 0, this is 1, this is 2. Okay, so now what we are going to do, we are going to compare all these three elements and we are going to see which one is the minimum. Is if the parent itself is minimum, we don't have to do anything. But if any other of them are minimum, we are going to swap the parent with the child, because parent must be the minimum of all the children and the parent themselves. Okay, so what I mean by that is we can clearly see that 70 is greater than 20 and 30, and which one is the smallest among them? It's 20. So we are going to swap 20 and 70. So 20 or 70 are swapped, 70 will come here and 20 here. So what we did, the third step was find minimum. If it is not parent, then I swap parent with minimum. Okay, so this is what we are going to do here, and we are going to do this until we achieve the heap order property. So now again, let's see, is 70 the minimum of these three? No, it is not. So which is the minimum? The 40 is minimum. So we are going to swap this 40 and 70. Now what we can see that is we have achieved the heap order property again. So this is how we use down heapify and remove. Now we can clearly see that the left child is greater than right child. So as I stated earlier, it is completely possible. So it is still is a heap which with following heap order property, and it is a complete binary tree. Okay, now the thing is, how does this remove work in login time complexity? So the swap operation is done in own time complexity. The remove operation is also done in own time complexity, because we are removing from the last position, and the only thing that is running in login time complexity is the down heapify itself. So when we use down heapify, it would traverse the whole tree, so that would take login time. That is why this O1, this O1, this O login, so overall complexity would be login itself. Okay, so this is how both remove and add work in login time complexity. Okay, I hope my explanation was clear. So before writing, let me just show remove once again. So let me just say I want to remove, call remove again. So what would happen? Now the smallest element is 20, right? So 20 would be removed. So to do that, I'm going to set 20 and 60. So let's do that. 20 to 60 the last element. Okay, so 20 would come here, 60 would be here. Now what we can see that is, what we're going to do is we're going to remove 20, which is second step. Now we are going to find minimum of these three. Which is the minimum of these three? It is nothing but 30. So we are going to swap 30 with the parent. So 30 would come here, so 60 would come here, and 30 would come here. Now it has again regained the heap order property. So this is how we perform remove operations. Now let us write a code for that. So the first thing, let us write the easy part first. So what would be the size of the priority queue? That will be nothing but the size of the array list. Okay, so data dot size, we are going to return this. Okay, now for peak, as I stated earlier, peak would return the element with the highest priority, right? And what is the element with the highest priority? It is nothing but the root node, and the root node is always at the first index of the array list, or we can say 0th index of the array list. So if we are first going to check if size is 0, if it is 0, what we are going to do is we are going to print underflow as stated here in the question. So we have to do that underflow, and I'm going to return -1. If size is not 0, what I'm going to do is I'm going to return data dot get 0. So the first element of the array list is the root node. Now moving on, let's see our add method. So in add method, as I stated earlier, we'll perform two operations. First one would be add to the array list, and second one would be we perform the up heapify. So to do that, let us see. First thing, we add the element to the array list. So the array list is data, so data dot add val, and now we call our up heapify with size -1. So let us now define our method. So public void up heapify, and here we are going to specify an index. So let us see int idx. Now first thing what we did was get the parent index. So int parent index would be parent index -1 upon 2. So let us write like this. So we have gotten the parent index. Now we'll check if the value of the element at current index is smaller than the value of parent index, because this is not desired, right? The value of parent index must be smaller. But if this is the case, so let me just take it to the editor so it is more visible. Let's write it here. Okay, now let us continue. So if the element at the current position is less than the parent index itself, so the element at the parent index, if this happens, what we are going to do is we are going to swap these two elements. So let us do that. We are going to swap idx pi, and we are going to call our up heapify with pi, actually with idx. Okay, because this idx is not now, actually it would be pi, because we have to consider now the next index, right? So for example, I was getting a bit confused, but let's see why I changed it to pi. So as we can see, when we are adding, I use 7 initially, then I used 3, and then I used 1. So that is why we have to change the IDX to pi for the next step. Now what I'm going to do is at the base case. So as stated earlier, when this would stop, it will stop when I reach the root node. So if idx is equal to 0, that is we are the root node. I'm just going to return. Now we have to write the swap function. So to do that, this swapping is a bit different from swapping two integers. That is because we are swapping in array list. So uh, let's pay attention here. So public void swap, let's say I'm swapping elements at index I and index j. So these are not the element, these are the index of the elements. So what I'm going to do is I'm going to store the value of the element at I. So in temp is equal to data dot get I. This would give me the element at I. So this is the ith element, and I'm going to set the value of ith element as the value of jth element to swap them. Okay, I did this. Okay, so now I'm going to set the value of jth element as the ith element. And what is the initial value of ith element? It was nothing but temp. So I do this. Now I've swapped them. Okay, now the next thing what we are going to do is we are going to see how this works. So let us quickly see this. Okay, so let me do this. So 1 minute. Okay, so first of all let me just clip this, and we are going to quickly see how this works. Okay, okay, let's see this here. So what we can see from here is how this is working is that first thing which is happening is that, let us say we are adding here. Let us say we are adding here. Okay, so first thing we get the index of the parent. So this is 0 1 2 3 4, and we are adding at 5. So 5 minus 1 by 2, what this would be? 4 by 2. This is 2. So we've got the element index of the parent. So it would check, let us say this was 10 20 30 40 50, and let us say we are adding 15. So if we are adding 15, the value of the element which we are adding is 15. So the first thing that we did is we just added the value. Okay, so we have added 15 here. Now we call the up pp5, and the element at size minus 1 is nothing but 15. So it would check the value of 15 with the element of parent index, that is 30. So 15 and 30, it would check if 15 is less than 30. 15 is less than 30, right? So it would swap them. So let us swap them. So I swap them. Now this becomes 15 and this becomes 30. Now the new index that I used here is pi, so it would be passed with 2. So idx would be 2. Now the new parent index would be 2 minus 1 by 2, so it would be 0. So now this would be compared with 0. Is 15 less than 0, less than element at 0, which is 10? No, right? So we will just proceed. Now what happens is that we see that our new idx is which is called is as at 0. So what will happen is that this will not be, this would just return from here. Okay, so after idx is equal to 0, we have reached here, so we have traversed the whole tree. After this we will return from here. No swapping is done because this condition is not true. Okay, now the thing is, we have seen how to do the add operation. Now let us quickly see how we do the remove operation. So first thing, we are going to check if the size is 0. If it is 0, we are going to return -1 and print underflow. Let us print. Okay, and I'm going to return here -1. And if it is not 0, then what I'm going to do is, as I showed earlier, to do the remove operation, what steps did we follow was, first of all, we swap the elements at root and size -1. So that is what we are going to do. First of all, I swap the element at root, that is swap 0 comma size -1. Okay, now I call the remove method, which I will do by data dot remove, and I'm going to remove the last element. So I'm going to actually return the element with the highest priority because it has been swapped with the root, and root was the highest priority. Now I'm going to store this in val. So in val is equal to data dot remove size minus 1. Okay. So before returning this value, I'm going to call our, since here as you can see, after removing we find a minimum, and this will be done in the down heapify itself. So I'm going to call a down heapify with 0 index. Okay, and here I would just return val, and here I'm going to define the down heapify method. So public void down heapify, and here I get int pi. So what first I'm going to do is I'm going to define a variable minimum to find the minimum between the parent and both the children. So I'm going to initialize it with int min is equal to pi. So first thing first, I'm going to find the left index of left child's index. So what I'm trying to do is, after removing the last element, I'm going to check the uh, I'm going to find the children of these two. That is, I swapped it with the root node, right? So the remove the swapped element is here. I'm going to check find its children. So to get its children, I'm going to use the method that use the formula that I explained earlier, which was li is equal to 2 into pi plus 1. So if you're getting a bit confused, I'm going to explain this again. So just be patient. So first thing, I'm going to check that if the left child exists at all, because as we can clearly see, there may be possibility that there is no left child. Okay, so for 50 there is no left child, it doesn't have any child. So how do we check that? To do that, I'm going to check if li is less than data dot size. So if it is inside the less than this, so that means it has a child. If this is true, and data dot get, that is the element in the left child is smaller than the element of the parent, I'm going to swap li and pi. So no, actually it would not be swapped. Here what I'm going to do, I'm going to update the min as li. That is, this means the li is smaller than the parent index. So the element at li is smaller than the element at parent index, so the new minimum is li. I'm going to again check with right element, is the right element is smaller than li or not. So that would happen if li is, first of all I'm going to check if ri is less than data dot size. So what I'm going to do is that I'm going to, instead of data dot get pi, I'm going to use here data dot get min, because I have stored pi in min. Okay, now I have to compare with the new min. Okay, right? So that would actually compare with both of the parent and left child. Okay, so let's see. So first I check if right children exist or at all. Okay, if it exists, then what I'm going to check, if data dot get I, not I, it should be ri, and this should be li. So first of all, let me define ri. So ri should be 2 into pi plus 2. Okay, now if this is less than the current minimum data, if this is less than the current minimum data, I'm going to update the minimum as ri. Okay, so what I am going to do is, here if the minimum is not equal to parent index, that is the parent was not the minimum, if this happens, what I'm going to do is I'm going to swap the parent index with min, and I'm going to call down heapify again with the new min. Okay, so what this is doing is, let us see here. Okay, so let me scroll it a bit above. So let me first clip this one and let us take this to our page. So let's see how this is actually working. So yeah, so let's see. So as I said earlier, what this remove function is doing is that it is working in three steps. So the first was to swap the first element. So let us see. Let us quickly visualize it. 40, 50, 60, 70. Okay. Now what is happening? First it swapped the zeroth element with the size -1, which is 70. So I'm going to do that. I'm going to swap this and this. So we get here, what we get here? We get here 10 and we get here 70. Now we just remove it. I removed it. Data dot remove size -1. So this would be removed. Now the next thing is we call down heapify. So what this would do is actually set the minimum as pi. So the pi initially is 0, right? I passed pi as 0. Okay, so see, this is how we implement a priority queue using Heap. If you like the video, please don't forget to share and subscribe, and I'll see you guys in the next video. Thank you.